Let us now move to the physical property known as density. It's defined as the amount of material in a given volume of substance. Practically speaking, one can think of it as how much material by weight can I stuff into a given volume of space. Most people are familiar with its formula, D equal M divided by D, where D is the variable for density, M is the variable for mass, and V is the variable for volume. Density is an intensive property, meaning the value stays the same no matter how much material is present. For example, 1 ounce of water has exactly the same density as 1 gallon of water. Now that's opposed to an extensive property such as mass. 1 ounce of water weighs much less than 1 gallon of water. The value changes with the amount. So mass is an extensive property and density as an intensive property. So one of the typical types of questions density will address is, will it sink or float? And when you have two materials, the more dense material will sink and the less dense material will float. So you could just look on a table and see the values and take a good guess. You could look at the density of oil and see that it's less than the density of water and predict, hey, if you have an oil spill, the oil is going to float on top of the water. On the other hand, a nail will sink when you drop it in water. Why? Because iron is much more dense than water. Well, given density values can be important, how do we calculate density? Typically, there's two ways, algebraically or dimensional analysis. Algebraically means that you're going to use the equation D equal M divided by V. You're going to substitute in the values for the variables that you know, and you're going to solve for the one that you don't. Using dimensional analysis, you will set up the equation with the units of density and then perform the dimensional analysis or factor label method against that answer. The unit in science for density, at least in chemistry, is almost always grams per milliliter. So let's look at a simple example and a typical example. Here's an easy one. 11.2 milliliters of a liquid was weighed by difference and found to have a mass of 9.50 grams. What is the density? To solve this algebraically, you nearly need the formula. And this is an easy one. Why? Because it gives us volume, it gives us mass, and what we're looking for is already isolated. So essentially, you're using an algebraic equation, but you don't have to do any algebra. So here we go. What's the mass? 9.50 grams. What's the volume? 11.2 milliliters. And when you multiply those out or divide those out, you get 0.848 grams. Working this out using dimensional analysis, how many grams per milliliters? That translates what is the density. I need something with a G in the numerator. I see I have a 9.50 grams, a given piece of data. And I need something with a milliliter in it. And I do see I have 11.2 milliliter. And using dimensional analysis, you see we have 9.50 divided by 11.2, exactly what we had the other way. And we're going to get exactly the same answer when we divide it out. Well, let's consider a more typical problem. The density of 55.64 grams of a material is 21.4 grams per milliliter. What is the volume? Working that out algebraically, we can't simply substitute. What do we have to do? Because we are looking for volume and we know these two, so we now have to perform a little algebra. And we have D times V equal M, but wait, we need to do a little more algebra and know that V equal M divided by D. And now we substitute in the mass is 55.64 grams and the density is 21.4 grams per milliliter. And when we work all of that out, we get 2.60 milliliters as the volume. Working the same problem out algebraically, we're looking for the volume, and the unit of the volume is milliliters. So we look at our data and see, do we have anything with the ml in it? Well, we do. We have a milliliter there. But remember, with dimensional analysis, this has to be written as a conversion factor. So this would be written 21.4 grams per milliliter. Remember, / line has to be written as a horizontal line. So I need milliliters in the numerator, so I'm going to use the conversion factor this way. In 1 milliliter, there's 21.4 grams. So I have the unit that I'm looking for has showed up. What remains to do is to get rid of the G that's in the bottom. And it just so happens I do have a value with a G, and it's 55.64 grams. It's a piece of given data. Notice I now have exactly the same numbers. 55.64 divided by 21.4. And since it's set up exactly the same way, I'm going to get exactly the same number. So why do I say working with dimensional analysis is easier? Notice, algebraically, you had to, 1, know the formula. Number 2, you had to know how to do algebra. And number 3, you have to know how to handle units that are awkward, such as this milliliter is in the denominator of the denominator. So you have to know how to do those 3 things successfully to be able to work problems algebraically, at least anything other than a straight plug and chug. Notice, with dimensional analysis, this was no harder than any other problem. Set up the unit that you're looking for, and then arrange your data so that only that unit winds up showing up. And then you multiply, divide out. Much easier. It's the same process every time. Notice with dimensional analysis, I didn't even need to know the formula. I just had to match the units. All I need to know was the unit of the answer I was looking for. And here's a clue. If you take a multiple choice test, usually you will be given the unit of the answer. And so you can just use what's written as the test to even set up your problem. Much less skill required, much less memory required. And finally, if the factor label method, if dimensional analysis works better or is easier than solving things algebraically, can I always use it? Well, the good news, at least for this class, is with one exception, in that temperature conversion, dimensional analysis will work on every type of problem you're going to come across this semester. In other words, if you don't have a clue how to do algebra, but you're willing to learn dimensional analysis, you don't need to worry at all about your lack of algebraic skills. You'll do just fine. But you must know how to do dimensional analysis and do it well.